我一个人在
Hello? Hello? So for student 19, can you hear me? Student 19, can you hear me? Hello? Okay, good. So let me start this recording. Okay, good afternoon, ladies and gents. Time for us to start our class today. So first, I think all of you have already finished your quiz like last week. So quiz 2. So I hope you have all got very good results. For those of you who would like to consult, let me to help you go through your quiz paper. You have to email me. Okay, you have to email me. Now I cannot go through your quiz paper because the makeup quiz has not been conducted. But I think it will be conducted this Friday, right? So maybe you can, so on Friday, you can send me an email so that I can ask OAS to return your quiz paper so that we can do the consultation next week. Okay, but do remember, if you would like me to go through your quiz paper, you have to let me know. Okay, you have to let me know. So similar to what we have done for our quiz 1. Okay, for quiz 1. So for today, I'm going to continue talk about quantum physics. Basically, I will talk about 4 chapters. From chapter 3 for chapter 7. Chapter 3 for chapter 7. Okay, so that's the first thing I would like to talk about is the so-called quantum scattering. Quantum scattering. Hello, may I have your attention, please? Okay, so that's for quantum scattering. So first, you have to understand the concept of photon. The concept of photon. So this is what I have already introduced. Last week, right? So in black body radiation, we have already learned photon. As I said, photon is actually the atom of light. Okay, you can treat photon as an atom of light. So that for each photon, okay, so which means light is consists of a number of or photon. When you divide the light into infinitely small segments, the smallest pieces of energy you will get is a photon. Okay, the smallest pieces of energy you will get is a photon. Okay, so this is why we say it's atom of light. Okay, the photon's energy is only proportional to the frequency. The photon's energy is only proportional to the frequency. Okay, so this E here equal to H times F. This E here equal to H times F, proportional to the frequency. And then the moment of photon P, okay, equal to E divided by C. The energy divided by the speed, energy divided by the speed, okay, equal to H divided by lambda, okay, inversely proportional to the wavelength. Okay, this is the momentum of photon. This is the energy of a photon, okay. One is the momentum, one is the energy of a photon, okay. So you know, actually the concept of photon, I would say, is a very revolutionary concept in quantum physics, okay. This is also why Planck won Nobel Prize. Okay, so you know when Planck used a photon to describe, for example, this is Planck's law. Okay, Planck's law, and he proposed the idea of photon. The energy of photon can only be, the energy of light can only be transmitted, in terms of photon. At that time, you know, a few people believe him. Okay, so this is why, okay, when people use photon to explain some physical phenomenon, normally that guy will win the Nobel Prize. So I think Einstein is a very good example. When Planck proposed the idea of photon, okay, the idea of photon is proposed by Planck with Einstein. Then Einstein used the concept of photon to explain the photoelectric effect. Okay, so as I said, photoelectric effect, let me remind you, is when we incident the light onto a piece of metal. And the metal may eject photoelectron, may eject electron to the free space. Okay, but whether this effect can eject the electron does not depend on the intensity of light you enter onto the material. Okay, so people find it very confusing, but it only depends on the frequency of photon. Only when the frequency of photon is high enough, you can get photoelectron. Okay, and that people does not know how to explain that phenomenon. Einstein used the idea of photon to explain, to provide a physical explanation for that phenomenon. So that he won the Nobel Prize. Okay, then, okay, Compton use this kind of photon to explain another effect, which is Compton effect. So you can compare Compton effect with photoelectric effect. Photoelectric effect is when, okay, the energy of photon is totally transmitted to the electron. Okay, the energy of photon is totally transmitted to the electron. So the photon disappears, we get a photoelectron. Okay, photoelectron. But Compton experiment is okay. Interact with photon, they can exchange energy. So what Compton found that when we incident the light, okay, onto a material, as long as this material has free electron, for example, this is a kind of metal or graphite. Graphite also has free electrons. Then what Compton found is, okay, when we incident the light onto this free electron gas onto this material, then the output, the frequency of the output light will no longer remain the same as the incident light. Will no longer remain the same as the incident light. So why this phenomenon is changed? So you can visualize when we transmit the light through a pieces of glass. If the incident is red light, output is always red light. If the incident is blue light, output is always blue light. Right? The frequency of light will remain unchanged when it transmits through pieces of material. This is what we learn from traditional optical experiments. When we use that either water or glass, once it transmitted, the frequency of light will remain unchanged. But then what Compton found is that, okay, if you continue to increase the frequency, as long as the wavelength or the frequency of the photon reaches X-ray, for example, this is X-ray, high energy photon, very small wavelengths, okay, several picometers, several tens of picometers. Then in this case, he found that when light now transmitted through this material, its frequency will no longer remain unchanged. It will change. So what Compton found that, okay, if I incident light, for example, from bottom to the top, and then measure the wavelength of the output light. Okay, so if we are directly working at the forward direction, which means the transmitted light ray and the incident light ray, their angle is zero. Then he found, okay, this agreeing with traditional prediction, okay. addition with transitional prediction. Okay, so the output light does not have any frequency shift. But then if you are married at some other angle, what the Compton found that, okay, then the output frequency lambda prime will no longer be the same as lambda naught. Lambda naught is the incident light wavelength. And then this lambda prime will become bigger and bigger when you increase the angle between the transmitted light and the incident light. So which means when X-ray incident upon this material, it will be transmitted everywhere. So it's no longer remain as a single beam, it will transmit it everywhere. So at the 0 degree, you have the output frequency wavelength unchanged. But at the other angle, the output wavelength will increase with increasing angle, Okay? So this is what Compton found in the experiment. Okay, the output light frequency will be shifted from the incident light frequency, and the amount of frequency shift is given by the so-called Compton shift equation. Lambda prime minus lambda naught equal to this lambda c times 1 minus cosine theta. Okay, lambda prime, this is delta shift. As I said, lambda prime is the output light frequency. Lambda naught is the incident light frequency. So that this delta lambda is what we call the wavelength shift. It's always equal to a constant times 1 minus cosine theta. A constant lambda c times 1 minus cosine theta. This lambda c is given by h divided by mc. M here is the mass of electron. Okay, so it's about 2.4 picometer. Okay, 2.4 picometer. So that, you know, as I said, in quantum physics, in each chapter normally I will highlight some important equation for you to apply, for you to solve the final examination question. So that for Compton effect, this is the most important equation. Okay, this guy is the most important equation. As long as you found that, okay, this question has to be about Compton effect, this equation will always be applied. Okay, will always be applied. So that once you realize the question has to be about Compton effect, always write down this equation, then you will be awarded the marks. Okay, this is the first equation. Show you when light incident upon a certain material, how its wavelength will be shifted for out of the light. So for Compton scattering, of course, this is the most important equation. Apart from this equation, we have some other, two important equations. Okay, as I said, for Compton effect, this equation will always be tested. This equation may be tested. Okay, this equation is talk about the transmitted photon, and then this equation talk about the scattered electron. As I said, so Compton found this in experiment, but how to experimentize the frequency will shift? How? So that Compton also use the idea of photon to explain this phenomenon. So he applied first the conservation of energy, and then the conservation momentum between photon and electron. So that he proved this formula. So that's the conservation of momentum he found, he used in his theory. Is given by this equation. What he found that, okay, in the beginning, I only have the incident photon and the electron is at rest. Then after scattering, the scattered photon and the scattered electron, their momentum has to be conserved with the incident photon. So that along for incident photon, along the propagation direction, y direction, the incident photon's momentum is h divided by lambda naught. So while after it transmitted through, the momentum of incident photon was transmitted to the momentum of the scattered photon and the scattered electron. So that they have to satisfy these two equations. This is what we call the conservation of momentum. Okay, so that if the question asks you something about how the electron will be scattered, you have also to apply these two equations for the conservation of momentum. Okay, conservation of momentum. Any question? So if no question, now I will show you some tutorial on the past examination paper to show how to apply actually, the Compton shift equation and the conservation of momentum. Okay, so question 1. Here we have a photon with a wavelength lambda. Incident photon has a wavelength lambda. It scatters off a free electron at rest. Okay, so this is a typical keywords for quantum scattering, free with a photon scattered of a free electron. Okay, photon scattered of a free electron. These are keywords for you to identify. This question has a quantum effect. Okay, so maybe in the final examination, it will not say, okay, this is quantum effect or quantum scattering, but it will let you know a photon scattered off or scattered from a free electron. Okay, then these are keywords. This question has a quantum effect. Okay, first thing. So that from the first sentence, we will be able to know, okay, this is quantum effect. Then it will producing a second transmitted, so a transmitted photon lambda prime here. So this transmitted photon will then scatter off a second electron at position B. Then it will produce a third photon with a wavelength lambda double prime. And this lambda double prime just move in a direction opposite to the original incident photon lambda. Then the question wants us to determine what's the value between lambda double prime minus lambda. So what's the wavelength shift between the third photon and the original incident photon? Okay, what's the wavelength shift? Okay. So clearly, as I said, this question tests us about quantum scattering. Okay, tests about the quantum scattering. So that for quantum scattering, as I said, the first thing for you is to write down this quantum frequency shift. Okay, the formula for the wavelength shift. Okay, we have this lambda prime minus lambda equal to h MEC times 1 minus cosine theta. This is quantum shift equation. So now we found the relation between lambda prime and lambda. But what the question wants is lambda double prime and lambda. So that we need to look at the second electron, apply the quantum shift equation again. So now this is the question I would like every one of you to think about. At the position at the electron B, the wavelength shift should be lambda double prime minus lambda prime or lambda double prime minus lambda. What is the wavelength shift at the second electron B? What's the wavelength shift at the second electron B? So on the left hand side of the equation, I should write down lambda prime or lambda double prime minus lambda prime or lambda double prime minus lambda at the second electron. What do you think? At the second electron, what's the wavelength shift here? Sorry? Sorry? Yeah, what I'm asking is, okay, at the wavelength shift from at the electron B is from lambda prime to lambda double prime or from lambda to lambda double prime? Sorry? So the quantum scattering, what does quantum scattering mean? The transmitted wavelength will shift from the incident wavelength, right? Then which is the incidence? Yeah, this should be lambda prime. So that for at the second electron, of course, what I should write down is lambda double prime minus lambda prime, because transmitted photon, this is the incident photon for electron B. So that on the left hand side of the equation, what I should write is lambda double prime minus lambda prime. Then how about the right hand side? The right hand side, what is the angle between the incidence and the transmitted electron? Yes, very good. As I said, the angle is always measuring the incident direction and the transmitted direction. Now, lambda prime is along this dashed line, lambda double prime is anti-parallel, so that this pi minus theta is the angle between the transmitted and the incident electron. So that the second quantum shift equation should be written this way: lambda double prime minus lambda prime equal to 1 minus, so this is constant, okay, times 1 minus cosine pi over theta. Cosine pi over theta is minus cosine theta, so that is equal to this constant times 1 plus cosine theta. Okay, any question? So if no question, now this equation gives us a relationship between lambda double prime and lambda prime. The first equation gives us the relationship between lambda prime and lambda. So that you plus this two. Okay, so this lambda prime and minus lambda prime cancel out each other when you plus them together. Okay, equation 2 plus equation 1. The right hand side is what we want. This is delta lambda. The left hand side, the right hand side is okay. We plus this guy and this guy together, so it becomes 2h divided by MEC, or 2 delta lambda. Okay, it's about 4.8 picometer. Okay, 4.8 picometer. Okay, any question? Any question? Okay, so this is the first equation show you how to apply this quantum shift equation. Okay, what you have to understand is okay, what is the corresponding wavelength shift? Okay, so now let's look at the second example. So here we have an incident photon with a wavelength lambda scattered by a rest electron. Okay, still photon scattered by a free electron or photon scattered by a rest electron. That are keywords for quantum scattering. Okay, for quantum effect. Then after scattering, the wavelength and the scattering angle of this scattered photon become lambda prime and theta equal to 90 degree. Theta equal to 90 degree. I want you to express the angle of scattered electron with respect to the incident photon in terms of lambda and lambda c. In terms of lambda and lambda c. So as I said, this question here has to do about scattered electron. So that apart from this quantum shift equation, you have also to apply the conservation of momentum. Because only in the conservation of momentum, you have the contribution of the electron. So actually, this is the picture we are looking at. This is the picture we are looking at. In the past, I have an incident photon and the electron at rest before incidence. After incidence, the photon has a wavelength lambda prime, and the electron is no longer at free, is no longer rest. It moves in this direction phi. Okay, in this direction phi. So that in order to find the relationship between lambda prime and PE, we have to apply the conservation of momentum. Okay, the conservation of momentum. So first, you apply the conservation momentum along x direction. As I said, before incidence, the electron is at rest, so that the electron does not contribute to any momentum. So that before incidence, the total momentum along x direction is just p photon. This h divided by lambda, right? H divided by lambda is the momentum of photon. Okay, it's also the total momentum before the photon and the electron before the incidence. After incidence, it has this transmitted photon and this scattered electron. Their x component has to be the same as the original one. But this photon p prime does not contribute to any momentum along x direction because this photon 90 degree with theta equal to 90 degree, okay? So which means is exactly transmitted along y direction. So it has zero momentum along the x direction. So only the scattered electron will contribute to the x momentum along x direction. So it's PE times cosine phi. Okay? So that originally my momentum along x direction is h divided by lambda. After scattering, the momentum becomes PE times cosine theta. This two has to be the same. So that my h divided by lambda need to be PE times cosine phi. Okay? This is the first equation. So the second equation is we apply the conservation of momentum along the y direction. The conservation of momentum along the y direction. So the conservation of momentum now, let me ask you this question. Before scattering, what is the momentum along y direction? Before, very good, it's zero because it's the momentum of the photon and the rest electron. The conservation of momentum, so along y direction is zero. So now, which means now my p photon prime minus PE times psi is likely to equal to zero. Okay, right? So that this equal to zero, which means my p photon prime, as I said, p photon prime equal to h lambda prime minus this PE sin psi equal to zero. So which means this has to equal to h divided by lambda prime lead to equal to P times sin phi. Okay. Now, what the question want is only want us to find the scattered angle phi. Scattered angle phi. So that we use equation 2 divided by equation 1. We can cancel out this PE. We can get, okay, tangent phi. We can cancel this PE and also as well as H. We can write tangent phi as a function of lambda divided by lambda prime. But this question want is a lot express this guy in terms of lambda and lambda prime, but lambda and lambda c. Lambda c is, what's in the Compton shift equation. Clearly here we need to apply Compton shift equation. Okay, Compton shift equation. Okay, so in Compton shift equation, I should set my theta equal to how much? According to this question, 90 degrees, right? Because the question said it's perpendicular, so it's theta equal to 90 degrees. So that according to Compton shift equation, my lambda prime minus lambda lead to equal to lambda c times 1 minus cosine theta. Theta equal to 90 degrees, so that this guy is 1 minus 0. I get lambda c. So that my lambda prime should equal to lambda plus lambda c. Lambda plus lambda c. So that tangent phi just equal to lambda divided by lambda plus lambda c. Tangent phi equal to lambda divided by lambda plus lambda c. Okay. So any question? Clear? Any question here? Hello, if you have any question, raise your hand. How about student 19? Any question? Any question? No question? Okay, good. Let's look at one more example. Okay, so this is a past examination paper. Here we have a photon with a wavelength lambda naught incident onto an electron that is initially at rest. Okay, again, photon incident, photon scatter of an electron at rest or scatter of a free electron. Okay. So may I have your attention, please, ladies and gents? Yes, I found some students already fall asleep. So that you should okay, pay attention here. So it's okay, okay. So if you have any question, you just raise your hand. So after interaction, okay, the photon and the electron. So after the interaction between the photon and the electron, the photon will scatter exactly in the opposite direction with respect to the incident electron. Okay, now what does this mean? Photon scattering exactly in the opposite direction as the incident photon. So which means my theta is how much? Very good, 180. Okay, this is a clear indication that the theta is 180. Then the question wants you to express the momentum and energy of the scattered photon in terms of lambda naught, and then express the momentum and kinetic energy of the scattered electron in terms of lambda naught. Okay, so let's solve part 1 and part 2 one by one. So clearly this is Compton effect, right? So as I said, for Compton effect, the first thing you have to do is to apply the Compton shift equation. Compton shift equation. Okay. Lambda prime minus lambda naught equal to this h divided by MEC, so which is lambda c, times 1 minus cosine theta. So you already realize that in the question, scattered electron transmitted in the opposite direction relative to the incident one, which means theta is 180 degrees. So that I just set my theta equal to 180. So that clearly cosine 180 equal to minus 1. So that I can get lambda prime minus lambda naught equal to this 2 lambda c. Okay, 2 lambda c. So from here, okay, I will have a question for you. So some student comment on from the Compton scattering, from the Compton shift equation, that the wavelength shift can be any integer larger than 0. True or false? The wavelength shift can be any, not only integer, can be any positive number larger than 0. True or false? Can this wavelength shift be any value? No. Very good. So we should have a maximum value, right? What's the maximum value?
Lambda.
Sorry?
It should be lambda. The original wavelength.
No, the maximum wavelength shift. So which I mean lambda prime minus lambda log. What's the maximum of this wave velocity shift? Your content is a minimum wave velocity shift.
Lambda prime.
Yeah, lambda prime, the maximum lambda prime should equal to how much? So as you can say, lambda prime, wave velocity shift is this lambda prime minus lambda log.
Oh, lambda not plus the one on the right.
Yes. So what is the maximum of this value? Wave velocity shift is this value, right? Can this value be any number larger than 0? So lambda prime minus lambda log, can it be any value larger than 0? Any idea? Any idea? Or what I mean is, my question mean is, so lambda prime minus lambda log equal to this guy, right? Will this guy has a maximum value? Clearly, this guy will have a maximum value because cosine theta has a maximum value and a minimum value. If I want this guy to choose its maximum value, I theta should set equal to how much? Yes, very good. Cosine theta equal to -1, so that this guy will reach the maximum value, 2 lambda c. So which means in content shift equation, it tells my lambda prime can only be a value between lambda naught and lambda naught plus 2 lambda c. Okay? So which means the maximum wave velocity shift should be always smaller. The maximum wave velocity shift is 2 times lambda c. That happens at theta equal to 180 degree. At theta equal to 90 degree, this delta, this wave velocity shift equal to lambda c. Okay? So that at 180 degree, I will reach the maximum wave velocity shift. Okay? So my lambda prime minus lambda naught equal to 2 lambda c. Okay? Equal to 2 lambda c. This is when the maximum wave velocity shift happens. Okay, so from this equation, we will be able to write my lambda prime as a function of lambda naught. As a function of lambda naught. As to the momentum, my p prime should equal to minus h divided by lambda prime. Why I have a minus sign here? Because it's opposite 180 degree, right? My magnitude is p prime. My magnitude is p prime is equal to h divided by lambda prime because it's in 100 theta equal to 180, so not ideal to times cosine theta, cosine 180. So it's minus this guy. So E is the energy. Okay, E does not have any direction. So it's directly h divided by f, which is hc divided by lambda prime. So I get p prime and E prime. Okay. So after like content equation, I can directly get the momentum and the energy of the photon, of the scattered photon. Now, let's look at the second one. Okay, let's look at the second one. What I want here is the momentum and the kinetic energy of the scattered electron. As I said, anything related with the scattered electron, we have to apply the conservation of momentum. So when we apply the conservation of momentum around the, so if we assume the electron is scattered off by angle phi, apply the conservation of momentum along y direction, okay, along y direction. So you can say, so of course in the past, my incident photon lambda naught along x direction. Incident electron is at rest, so that the total momentum along y equal to 0, okay? Total momentum along y equal to 0. So that the momentum along y direction after the scattering should be contributed from lambda prime under this way. So the momentum of this photon along y prime is h divided by lambda prime times sine 180 degree. Okay, so it minus, okay, p sine phi should be equal to 0. So which means my h divided by lambda prime times sine 180 should equal to p sine phi. Because sine, here my sine 180 degree equal to 0. Sine 180 degree equal to 0. Okay, so this means my phi should also equal to 0. Okay, the first equation gives us phi equal to 0. So the second equation is the conservation of momentum along the x direction. So initially, my momentum, total momentum is h divided by lambda naught. incidentalized momentum. Okay, then it should equal to h divided by lambda prime cosine 180 degree. Okay, so this is the y. So there is a minus sign because okay, it is h divided by lambda prime times cosine 80 degree. Okay, so this is the momentum. This is the momentum of the electron. Oh, sorry, this is the momentum of the scattered photon plus p cosine phi. Momentum of the electron along the x direction. Okay, so that because the momentum of the momentum has to be conserved, so that my h divided by lambda naught, which is the total momentum before incidence, need to equal to the total momentum after the incidence. So that I substitute the lambda prime here, So the first equation gives us phi equal to 0. Here I just substitute lambda prime. I calculate in previous case into this equation. I will be able to get what my PE it is. Okay, this is my PE. Okay, so now I get PE. This is something I would like to highlight to you. When you get PE, how can we calculate the energy of the electron? So in the past, what we do is always use PE squared divided by 2m, right? Because PE equal to mv, energy equal to half mv squared. So PE squared divided by 2m is actually the kinetic energy. But that formula only true for classical, mechanics, classical physics. For quantum scattering, my electron here move very fast. So that's the formula for classical physics is no longer valid. In this case, the energy of the electron has to be calculated by the energy of the incident photon minus the energy of the scattered photon. Okay, you need to use this way to get the kinetic energy of the electron, but rather use the momentum to directly calculate the KE. Okay, that's wrong. So in quantum scattering, the classical formula for the kinetic energy half mv squared is no longer valid. You can only apply this formula KE equal to the incident photon's energy minus the scattered photon's energy to get the kinetic energy. Okay. So here we have to apply the theory of relativity here. So this is the only case in our class where the classical formula is not applied. Okay. Half mv squared is not applied in quantum scattering. Okay. So here, as I said, when you found the question asks you to find the kinetic energy of the scattered electron in quantum scattering, then do not apply half mv squared. Half mv squared is no longer valid. You have to only use this way. This is the only correct way. This is the only correct way for you to calculate the kinetic energy of the scattered electron. Okay. So in quantum theory, repeat 3 times. I already repeated 3 times. Okay. Here, pay attention to here. Kinetic energy of the scattered electron equal to the energy of the incident photon minus the energy of the scattered photon. Okay, no longer equal to half mv squared because of the theory of relativity. So now, any question? Yes.
Regarding part I remember there's one part where you say in front there's a minus sign in front of it. So if let's say, because for this reason, the thing reflects back also. That's why there's a minus sign in front.
Yes.
Let's say if I were to change the question a bit, I say the thing reflects back 135 degrees.
135 degrees, then it becomes cosine 175.
Yes, will there still be a minus sign in front?
So that means in this way, okay, so if it's minus 135, right, then of course cosine 135 there is still minus 1. But in this case, it not only has the x component, it also has a y component. You have to also to times, so which means along x direction, so along I direction, is this guy comes cosine 135. Along y direction, which is j direction, it is this guy comes sine 135.
So you always have to consider both the I direction.
Yeah, and the j direction. Yeah, that's right.
Okay, before you actually consider whether you put that.
Yeah, that's right.
On normal circumstances, the sine 180 is always minus.
Yes. It's always minus on x, but 130 is positive on y. Sine 180 equal to square root over 2. Okay. Cosine 135 equal to minus square root over 2. So x component is negative, y component is positive. Okay. Good. So So then atomic spectrum. So before talking about atomic spectrum, so I think this is related. This is related with the experiment you have done, on diffraction grating. So for the experiment we have done on diffraction grating, we landed a kind of source. Okay. So we found that the discharge of a specific chemical element will only emit light at some discrete wavelengths, right? This is what you learn in your diffraction grating experiments. So if a certain chemical element discharge, it will always emit light at some discrete frequency, not white light over the whole continuous spectrum. It will only emit at a discrete frequency. Okay. So that people, just want to explain why, for example, the discharge of this hydrogen or helium can only happen at some discrete frequency. So that we need to use our atomic spectrum. So what the first people used to do is to consider hydrogen atom. So for hydrogen atom, so when people do experiment, people found two interesting phenomena. So first, its emission. The frequency emission can only happens at some discrete frequency. And also, what people found that the radius, because we have hydrogen atom. What is hydrogen atom? So it's an electron circulate around the proton. Okay, circulate around the proton. So that's if you just apply classical theory to consider, for example, the electron in circular motion around the proton. So we have this Ke squared divided by R squared. This is Coulomb force, serve as a centripetal force. So when you write down this equation, you will be able to find that R actually can be any value. Okay, depending on the velocity v. Okay, R equal to Ke squared divided by mv. So that which means R actually can be at any value. Okay, so in terms of v. But when people do experiments, they find out, okay, so what is this? R cannot be at any value. Okay, cannot be at any value. Even you change your v. They found that the R can only be discretized at several quantized value. Okay, several discretized value. Just like when the hydrogen atom can only emit light at several discrete frequencies. So at that time, people don't know how to explain this. And then Born, so who also win the Nobel Prize, okay. So Born from Copenhagen University, okay. He gives 4 assumptions to explain why the orbit of the hydrogen atom has to be quantized. So which means why Rn has to be discretized. He also used this 4 assumption to explain why hydrogen atom can only emit at some discretized frequency. And then his theory can be quite well with the experiment. Okay, so this is what Born's 4 assumption. So for atomic spectrum here, what we have to understand is Born's 4 assumption and the 4 important formula. Okay, 4 important formula and Born's 4 assumption. So for Born's 4 assumption, okay, the first assumption is actually the classical formula. He suggests that the electron circulate the nucleus circulate the atom, okay, is always undergo circular motion. And the centripetal force is given by the Coulomb's formula. Okay, similar to this picture. Then, in order to explain why the orbit has to be quantized, Born made an assumption that the electron circulate around the nucleus, its orbital angular momentum has to be quantized. It will quantize in this way so that mv times r, mv times r is the orbital angular momentum. Okay, momentum times the radius is what we call the orbital angular momentum. mvr is always equal to an integer times h divided by 2 pi. So this is the first assumption for. So he just think of this, to just assume this does not provide any proof. But he found that this assumption actually are quite well with the experiment. So that if you assume this is correct, you find a relationship between V and R, right? You find a relationship between V and R, which means you can actually write V as a function of R, and then you combine these 2 equations. You will be able to show R is always equal to n squared times A naught. A naught is what we call the atomic distance. Okay, it's about 0.53 angstrom. 0.53 angstrom. So that combine these two formulas, boiling point that my R always equal to n squared and this A naught and constant. These are going very well with the experiments. So that, just with the two assumptions, one successfully express why the orbit radius of the hydrogen atom has to be quantized. Okay, so this is Born's four assumption. So then, in order to emit white hydrogen atom, will only emit at several discrete wavelengths indeed another four assumptions. Okay, so first, if the electron state is a sun orbit, it will not emit light. But when the electron, jump from one orbit to the other, it will either absorb or emit photon. It will either absorb or emit one photon. And then the emitted photons frequency or the emitted photons energy is equal to the energy difference between these two orbits. Okay, the energy difference between these two orbits will give us the energy of the photon, so which will in turn determine the frequency of the electron. This is Born's third assumption. Then, what is the energy of each orbit? For example, this is EI and EF. Then it depends on the radius at which radius the electron is. Okay, so these are the three important formulas. The last important formula is how this energy E will be calculated. So E always equal to minus 13.6 divided by n squared EV. Minus 30.6 divided by n squared in EV. Okay, so which means if the electron is initially at n equal to 1, then it jumps to n equal to 3, so that you should equal, first find out E3 and E1, using E3 minus E1 to get the energy of photon, so that we will be able to get the frequency of the photon. Okay, so this is what owns the other two assumptions, help you to explain what is the energy of the emitted photon or emitted light. And then Born used this formula. He found that the emitted photons frequency are going quite well with what observed in the experiment. So for example, in visible spectrum, this guy corresponds to transmission from n equal to 3 or n equal to 6 to n equal to 2. This blue light is n equal to 5 to n equal to 2. Green light is n equal to 4 to n equal to 2. And red light is n equal to 3 to n equal to 2. Okay, so that if you use this formula, okay, set n equal to 2 and n equal to 3, and then do the minus, get the photons energy, you will find that it will exactly fall in this spectrum. Okay, it happened quite well with the experiment. Okay, so which means Born's assumption is correct. Any question? So if no question, as I said, for atomic spectrum, 4 important formula. Okay, 4 important formula. So for complex, that is 3 important formula. Complex shift equation and the 2 equation about the momentum conservation. Here, atomic spectrum, as I said, 4 important formula. Central pair force given by the Coulomb's attraction, quantization of the angular momentum. The other two is about the emitted photon. The photon's energy equal to the energy difference between two orbits. And each orbit's energy is given by minus 13.6 divided by n squared. Okay, just this 4 formula. Then you properly apply this four formula, you will be able to solve any question regarding the atomic spectrum. Okay, so now let's look at some questions. So question 3, here we have a monochromatic beam of light. It was absorbed by a collection of ground state hydrogen atom. Okay, ground state hydrogen atom. A collection of ground state hydrogen atom, which means I have many hydrogen atom. Okay, I have many hydrogen atom. So that after absorb this light, of course, the ground state hydrogen atom will all be prepared at some excited state. Right, it will be excited into a certain excited state. Okay, so then it will emit in such a way that 6 wavelengths are observed when the hydrogen atom is relaxed back to the ground state. Then the question wants us to calculate what is the wavelength of the incident beam. So as I said, if you want to calculate the incident of the wavelength beam, you have to need to know what are the energy difference between the two levels. Or here we need to know at which excited states the hydrogen atom is at. At which excited state the hydrogen atom is at. as I said, initially the hydrogen atom is at the ground state. After absorbing the photon, it was emitted into a certain excited state. So for example, if the hydrogen atom is just at the ground state 2, so when it relaxes back to ground 1, it can only emit this wavelength 2 to 1. No other wavelength is possible. On the other hand, if the electron after absorb the photon, it was excited into the excited state 2, n equal to 3, then how many wavelengths do you think it can emit? It can emit 3. Why? Because when we have a number of hydrogen atoms, not only one, some hydrogen atom may directly emit light from 3 to 1, directly emit this frequency of light so that it jumped back to the ground state. Or it will first emit to ground 2 and then ground 2 back to ground 1. So it has 2 channels to be emitted back to the original state, right? So either 3 to 1 or first 3 to 2 and then 2 to 1. So in this case, if this collection of hydrogen atom is prepared at the excited state n equal to 3, then it makes emit 3 possible wavelengths. Okay. Now the question tells us that it emits 6 possible wavelengths. Could you let me know what is the quantum number n of the excited state? It should have n equal to how much? 3, 4, or 5? Sorry? Very good. That should be 4. Okay. So this is what I would like to highlight for you. Okay. So let me write down something here. So that's for if my electron is at a certain energy level with a quantum number n, okay, my hydrogen atom is prepared at a certain energy level n, and then the possible wavelengths when this collection of atom was emitted back to the ground state, the possible emitting wavelength is actually n times n minus 1 divided by 2. Okay. This is what we call the possible emitting wavelength. So you can say if my n equal to 2, excited wavelength equal to 2. So here I need to have a collective hydrogen atom. Okay, if only one, this hydrogen atom will need to release back to a certain energy level. Only one wavelength is emitted. But if we have a number of atom, a lot of atom at this excited state, some will directly emit back from 1, some will emit from, for example, 3 to 2 and 2 to 1, and then we have a lot of possibility. Okay, so that in this case, if I have a collection of hydrogen atom, the possible emitting wavelength is always n times n minus 1 divided by 2. For example, when it's at 2, it can only emit 1 wavelength because 2 times 1 divided by 2 is 1. N equal to 3, 3 times 2 divided by 2 is 3 wavelengths. If it's at 4, 4 times 3, 12 divided by 2 is 6. Then if it's at 5, 5 times 4 divided by 2 is 4. Okay, but so it's 10. So if it's at n equal to 5, we can need 10 possible wavelengths. Okay, so in the past, we have a past imagination paper test about this. Okay, when it's at n equal to 5, how many possible wavelengths can the excited hydrogen atom emit? You have to commonize 5, also it's 10, and what are the value of the 10 wavelengths? Okay, you have to use this way to do the calculation. So that, as I said, because it emits 4 wavelengths, we can quickly tell that, okay, the excited state of the hydrogen atom is n equal to 4. So n equal to 4, it can emit 4 wavelengths, 2 to 1, 3 to 2, or 3 to 1, 4 to 3, then 4 to 2, and 4 to 1. So in this case, I will be able to emit these 4 possible wavelengths. So why this hydrogen atom will be, prepared at the n equal to 4 is because it absorbs a photon. So it absorbs a photon, then it jump from ground state n equal to 1 to ground state n equal to 4. So that we assume bonds for assumption. First, calculate the kinetic, the energy at n equal to 1. So which is this minus 30.6 divided by 1 square. Okay. And then at n equal to 4, it's minus 13.6 divided by 4 square. Then the photon's energy is equal to the difference between these two. The difference between these two, okay, EF minus EI, I can write down the energy of the photon in the EV, then times 1.6 10 to the minus 19, then I will change EV to joule. So HC divided by this joule, I will get what is my lambda. Okay, my lambda in this case is about 97.4 nanometers. 97.4 nanometers. So any question? Any question? So if no question, which that is very good. Now, if no question, I will ask you a question. Okay, I will ask you a question. So we know that when the photon's energy is exactly the same as the energy difference between, for example, 2.1, okay, then it will make the ground state electron to jump from the n equal to 2 excited states. Now, if I have a photon's energy, it's larger than the energy difference between 2 to 1, but smaller than the energy between 3 and 2. Will it be able to, make the electron to transit from 1 to 2? If the photon's energy is just between the energy level, so it's larger than the energy level difference between n to 2, but smaller than 3 to 1. Will this photon able to make the electron to transit from n equal to 1 to n equal to 2? Will or will not? So the answer to here is not. We have a past evaluation here test about this. He gave you the photon's energy and asked you whether this will be able to make the electron to transit. If it will, then it will transit from ground state to n equal to how much? Then you find that the energy is actually just between 2 and 3 here. So if you want to make the electron to transit from a certain energy level to the other, the photon's energy must be exactly the same as such energy level difference. Otherwise, it will not be able to make any transition. So even it's larger than this value, the transition from n equal to 1 to n equal to 2 is impossible. Okay, it must be exactly the same to that value. Okay. This is the other case is not that important, but I think it's also in the summary lecture, so that I briefly describe. So that if we hydrogen atoms, we have an electron circulate a single proton. If we have an electron circulate, for example, 2 proton or 3 proton, that is what we call ion. And then in this way, the Coulomb's attraction formula will be changed to this one, okay? Because now we have the number of protons. And then the corresponding energy of different energy level now is this minus 13.6 times first this square. Z is the number of electrons in the nucleus, okay, times this square divided by n square. Okay, so for hydrogen atoms, they equal to 1, so that we have directly minus 13.6 divided by n square. But if we have, for example, a number of proton, the number of proton in the nucleus, we have to times another this square in the numerator. Okay, so yes, this is one thing. So and then the third thing here is what we call this Schrödinger's equation. Okay, so in quantum physics, for example, in classical physics, we normally use energy and momentum to describe an object. When an object is moving, it will have a fixed energy and a fixed momentum. But in quantum physics, people are not interested in knowing, for example, the velocity, exact velocity, or exact energy of the for example, electron or moving particle. We use the so-called probability function to describe, for example, the electron. So, for example, the electron. So, what the people found that the probability function of the electron, which means so the probability function is what we call phi. Okay, and the corresponding probability density is this phi square. phi squared. So phi squared means the probability to find out the electron at a certain position. So you know phi is actually a function of the space X. For example, the space of X. And then phi has to satisfy a partial differential equation, given by the Schrödinger's equation here. So when you solve phi, you will get a space between the functions. And then phi squared will give you the probability of finding the electron at a certain position. So for example, if you want to find the electron within a certain interval A and B, what you do is to integrate this phi square from A to B to find out what are the probability. So of course, when you integrate phi from 0 to infinity or minus infinity to positive infinity, you will always get 1. Because the electron anyway has to be happening or space. Integrate from minus infinity to positive infinity, that means the whole space. So it's equal to 1. Okay, so this is the probability function. So that in the final examination, if the probability function is given, people ask you what are the probability to find the electron within a certain interval, you will be able to understand. That actually tests you to apply the integration. Okay, so here we have some, I have 2 questions, 2 examples here to illustrate this case. So first here we have so we know a wave function of the particle or probability function of the particle is given by this formula. Okay, given by this formula, and then you can quickly show when you integrate this guy from minus infinity to positive infinity, it will go to 1. It will go to 1. Okay, but this question wants us to determine the probability of finding this particle from minus A to positive A. So as I said, for this kind of question, the probability is equal to the integration of phi squared from minus A to positive A. So that what I want you is to do this kind of integration, this integration. So that according to the question, the question tells you 1 divided by 1 plus t squared is equal to arc tangent t. But clearly this integration given in the question is different from all integration keys. Okay, so in this case, actually you have to do some changing of variables. For example, here you just assume change of variable t equal to x divided by a. So integrate x from minus a to positive a. So similar to integrate t from minus 1 to positive 1, because minus a divided by a is minus 1. A divided by A is equal to 1. Then, as I said, my x need to be replaced by A times t. X replaced by A times t. Okay, here I put a pi, in front. So at the denominator, I should have A squared t squared plus A squared. dx is A times dt. So that A squared cancel off each other. Inside the bracket, I will just remain as 1 divided 1 plus t squared. So that I quickly know that this integration equal to arc tangent t. Arc tangent t from minus 1 to positive 1 is actually pi divided by 2. So pi divided by 2 divided by pi, I get 1/2. So that's the probability of finding this particle within minus A and A is 50%. Okay, is 50%. Okay, any question? So this is actually do integration and then compare with the integration that is given in the question. So in flow question, now I will talk about one of the past examination papers. I think this question is very difficult. Okay, so although it's not required by this class, but I will just want to show you. Okay, the probability function sometimes actually was tested in the final examination. For example, here 2 years ago. We actually tested this, okay? We have tested this. So now let's look at this question. So we have a particle moving on X, then its wave function is expressed by this way. When X larger than 0, it was exponentially decay. When it's smaller than 0, it's exponentially increased. So that the people want you to find out the relationship. The examiner wants you to find out the relationship between D and beta. And also want you to find out the probability of finding this particle. So the second question is the probability of finding this particle from minus delta to delta is just 1 divided by 2. Then want you to find out the relationship between delta and beta. Then finally, it asks you the probability of finding this particle from minus delta to positive infinity. Okay, 3 parts, 1 by 1. So you know the normalization condition, which means the integration of phi squared from minus infinity to positive infinity should equal to 1. So that this is what we do. Okay, we have to integrate this phi from minus infinity to positive infinity, and then set this guy equal to 1. This is what we call the normalization condition. So that because phi have different forms, you know, larger or smaller than 0, so that we need to divide the whole integration into 2 parts. So that from minus infinity to 0, we integrate, you know, e to the positive 2 beta x from minus infinity to 0. And then from 0 to positive infinity is e to the minus 2 beta x from 0 to infinity. Okay, from 0 to infinity. Okay, so that's the first integration. You will be able to show that, okay, it's actually integrated is just d squared divided by 2 beta times e to the 2 beta x from minus infinity to positive infinity. While the second part, you put this constant minus 2 beta in front, so that it becomes this guy. Then when you substitute 0 and infinity into this equation, you can say minus infinity, when it substitutes into this guy, it becomes 0. So that is 1 minus 0. 0 to positive infinity, when it's positive infinity, this guy is 0. So it's 0 minus 1 in this case. So that you quickly show that, okay, my d squared should equal to beta. My d squared equal to beta. Okay, when you combine these two equations here, you see that, okay, you can directly show my d equal to square root beta. So that this is the first part, okay, just doing the integration. So that for part 2, so for part 2 that we still do in the same way, just set this to 1/2 as a question set, so that now my minus infinity should be replaced by minus delta. Positive infinity should be replaced as a positive delta. Okay, this equal to 1/2. So that we substitute the guy in, so that this 0 becomes e to the minus 2 beta delta, and then positive infinity becomes e to the minus 2 beta delta. So that we get this guy. So when you do that, you will be able to find my e to the 2 beta delta equal to 1/2. So that you can find the relationship between beta and delta in this way. So this is solution to the second part. The last part, actually, we can easily do that. Is okay. What we have already shown is the integration of this phi squared from 0 to infinity equal to 1/2, and the integration from minus 1 to 0 equal to 1/4. This is what we do in part 1 and part 2. So that's the last part. When you want to find out the probability of minus 1 to positive infinity is actually equal to 1 divided by 2 plus 1 divided by 4, so which is 3/4. Okay, so this is the solution to the, you know, to this one. This is solution to this question. Okay, about the probability function. Okay, so because of the limitation of time, I will quickly jump to the last chapter. Okay, about the quantum box. Okay, so if you have any question regarding the probability function, so you do take a look at my solution. So normally the probability function is, okay, integrate to find out the probability. Okay, to find the probability. You look at the math there. If you have any question, you know, just email me to make an appointment so that I will explain to you. Now we have to look at the quantum box. So first we have to understand what is a quantum box. Okay. So you know, quantum box is we create a certain potential so that we can trap the electron only inside a certain region. So like hydrogen atom, we have used the Coulomb force to trap the electron. So it's a certain kind of, you know, potential. But in this case, the electron can still extend from I to 0 to infinity. But the quantum box is a different way. We create a certain potential so that the electron is only confined in a certain box. For example, from x equal to 0 to x equal to L. So this is what we call quantum box. Then what the people found that the electron inside the quantum box, okay, its energy is also quantized, same as what happens in hydrogen atom. So hydrogen atom, the energy, the orbital of the electron is quantized, so that the energy is quantized. So that the people find that in quantum box, the electron is orbit and energy is also quantized. But just the quantized value are different. The quantized value are different. Okay. So that the people find that the energy of each orbit of the electron in the quantum box is given by this constant h squared divided by 2ml squared times n squared. Okay, times n squared. So that m, of course, is the mass of the electron, L is the weight of the quantum box, H is the Planck's constant, and n is the arbitrary integer. Okay, so you know the electron inside the quantum box and the electron inside the hydrogen atom are more or less linear. Okay, it both is orbit and its energy are quantized. Just the quantized value are different. Okay, quantized value are different. In quantum box, the energy are quantized in this way. In hydrogen atom, the energy of the electron are quantized as minus 13.6 divided by n squared. Okay. Then, if the electron jump from between different energy level, it will also emit or absorb the photon. Okay. So for quantum box, as I said here, there is only one important equation. So is this how the energy is quantized? Okay. So that, as I said, this is the most important one. This is the most important formula. Okay, this is the most important formula for the quantization of the electron in a quantum box. So that's some other formula which is also relevant. Okay, maybe not that important as this formula is. Okay, the wave function of the electron inside the quantum box always take this form: a times sine kx. K is actually the wave number. When you solve Schrödinger's equation, you will be able to find that k is always equal to square root 2me divided by h. And then because the electron is contained in the quantum box, we know that k should always be quantized at n divided by pi l, so that this equation can help you to get what is my En. But as I said, this how the energy of the electron is quantized in quantum box is the most important one. So this is what you should you need to understand. What you have to understand. Okay. So yes, the box I highlighted as the most important formula. So that for quantum box, there are two important formula for you to understand, or for you to understand how to apply. So now I will have two questions to go through. So first, we have an electron with a wavelength lambda is absorbed by an electron confined to a quantum box. Okay, confined to a quantum box. As a result, the electron will move from state energy 1 to state energy 4. I want you to find the length of the quantum box as a function of the incident photons wavelength lambda. Then in the second part, I show you that then the electron will transit from energy level n equal to 4 to energy level n equal to 2. Then I want you to find out what is the corresponding wavelength of the emitted photon when the electron transits from n equal to 4 n equal to 2. So clearly, this is actually an application of this formula. For quantum box, En equal to h squared divided by 8ml squared times n squared. Okay. The first question wants us to find out this L. It tells you when the electron transits from n equal to 1 to n equal to 4, it will emit a wavelength. So which means in this case, we have to equal the energy of the photon to the energy difference between n equal to 4 and n equal to 1. Okay, so the energy of photon is hc divided by lambda. Here, hc divided by lambda. Energy difference between n equal to 4 and n equal to 3 is actually this constant here times 4 squared minus 1 squared, so which is 15. So clearly, this equation relate lambda and L together, so that you can just exchange this formula. Okay, you just do a little variation to this formula, you can find that my L equal to this guy. Okay, problem solved, right? So as I said, quantum box is similar to the hydrogen atom. So it normally asks you to find out the wavelength when the electron transmits from one energy level to the other in the quantum box. So what we do is find out the energy difference between two, between two orbits or between two energy, and then find out the wavelength. So this is what we do for the second part. So I want to find out the wavelength lambda prime when the electron transits from n equal to 4 to n equal to 2. So that here I just replace this 1 by 2, so that inside the bracket I have 4 square minus 2 square, so I get 12. Now, what is L? I have already calculated before, so that I just replace L by this guy. I will be able to find that my lambda prime is just 1.25 times lambda. Okay, so the emitting photons wavelength is actually 1.25 of the original incident light wavelength. Okay, just apply, the energy of the emitting photon equal to the energy difference between two energy. Okay, between two energy level. Any question here? Any question? Okay, so if no question, then here we have one past examination papers. Okay, the last question is one past examination papers. This was also tested 2 years ago. So as I said, for quantum box, maybe we have a lot of concept, but normally for quantum physics, as long as you understand what this question tested, okay, normally directly apply the formula, you will be able to solve the question. Okay. So here I have an electron trapped in a one-dimensional quantum box with a weight L. Then I let delta En to be the energy level difference between En and En plus 1. So which means my delta En equal to En plus 1 minus En. I want you to determine the value of N which yields the largest delta En divided by En. Then the value of N which yields the smallest delta En divided by N. And then want to ask you, will the weight of the quantum box affect the results you found in 1 and 2? So clearly, as I said, for quantum box, the first thing for you to do is write down its energy. Always write on this, you will be at least around 2 marks. Okay, 2 marks here. So En equal to this way. Then the question want us to find out what is delta En. So that you just replace, this delta En by En plus 1 minus En. For En plus 1, you replace this N by N plus 1. Okay, N plus 1 square minus N square, so that I will get 2N plus 1. 2N plus 1. Okay, and then this delta En divided by En, this constant cancel out each other. So it will just become 2N plus 1 divided by N square. 2N plus 1 divided by N square, then is equal to 2 divided by N plus 1 divided by N square. N can only be integer. Okay, N can only be integer. Now the first question wants us to find out the maximum delta En divided by N. Okay, so that you look at this formula, this guy here, 2 divided by N plus 1 divided by N square. Can you let me know this will increase of N or decrease with N? Increase or decrease with N? Any idea? Hello? Do you think this will increase with N or decrease with N? This formula, 2 divided by N plus 1 divided by N square. This increase with N or just decrease with N? Hello? Clearly, larger N will make this guy smaller, right? Smaller N will make this guy larger. So that if you want to get the largest value, you should look at the smallest N equal to 1. Okay, so when N equal to 1, my delta En divided by N will reach the maximum value, which is 3, because N equal to 1. So for the second question, okay, for the second question, I want this to reach the minimum value, so that I should look for the largest N. Largest N is N equal to infinity. N equal to infinity, 2 divided by infinity equal to 0. 1 divided by infinity square also equal to 0, so it's 0. So that clearly, the largest value should happen at the smallest N equal to 1, and the value is 3. Then the smallest ratio should happen at N equal to infinity. So where this delta En divided by equal to 0. This is what you have to comment here. So clearly here we have delta En divided by En only depending on n. So that's the last part. Want us to comment whether this guy is a function. So will be changed if we change L. So you will say, okay, L does not affect the ratio because according to our calculation, delta En divided by n is not a function of L. Okay, so problem solved. So clearly, I think both equations, okay, both questions here to help you to see that, okay, for quantum physics, as long as you identify the correct formula for apply, so normally you can directly solve the question, okay? So that here I have another past examination papers, but first it was not required by this tutorial. And also the limitation of time, I think it's already the time to end our class. So that, but I think this is also a good question. This is also a good question. Actually, so this is what I put up, what I said, 4 years ago. So solution here are provided. I hope everyone of you should try to take a look at the solution yourself, okay, to see more examples. As I said, for quantum physics here, we have a lot of chapters. I hope you should try to look at as many past examination papers as possible, okay, and try to digest the solution. If you have any questions, just let me know, okay? So if no question, the class can be dismissed, okay? So if you have any question now, it's the right time for you to ask. Okay, good. So any question?
No questions.
Okay. So you should try to do some revision yourself. Okay. So we have a lot of opportunity in the revision week to look at the quantum physics. So quantum physics, I think you have to solve some example, to solve some questions, to get some examples. No, I also sorry. The two past year paper. So the final examinations, I will also help you with some past examination preparations. Okay, I will also do that. But it will be good if you can, already prepared to look at this question. So that will make the effect in the matter. Okay. No problem. You're welcome. So the how your place? Which two? Good.
Okay.
Should be fine. So if you want presentation, do remember send on email this Friday. Okay. Presentation with you. If you want to do presentation with you, send me an email this Friday. Because the breakout is Friday, so after that, okay. Because of the time we so we don't pick up. Yes.
Thanks for the squeeze.
Oh, right. Oh, yeah.
Yes, come on.
How do you remember that? Okay, yes. What I think is I think I have a similar question, guys. In my also you have you look at my summary lecture. Sorry. What's the thing that? Yes. I know. No, it's not in this way. So it was it should be in how to say paragraph. But I think that decision is initially touched by everything. So let me see is initially that is connected of course. Yes.
Hey, Zui, stay back.
Initially,
Stay back.
He's very angry.
Gonna kick out.
Then we disconnect.
Daniel, can you unmute your mic, Daniel?
I think he kept it up. Just on for fun.
Daniel, you got any questions? Daniel? Last chance, Daniel.
Serious. In serious is only right? Go on, head to head. Bottom to bottom, this is the class. Serious is only one.
Okay lah. I also second. The one D one
This is imperative. Of course, imperative. Serious is only one, right? The only kind is fully up to So if we are serious, you remove this is also other than zero.
Bro, meeting right now.
So you look at this is right. Okay. So if it's head to head, one is always imperative. Okay. Am I correct?
Then how do you get the rotation across 26 degree? The cell of the
Sorry?
So the rotation across the 26 microfarad is 2 of the 7.
Yes, so you in this case, okay, it has first charge to 50 volt, right? To 50 volt. So which is the total charge, now this 26 times, okay, so actually times 10 to the minus 6, this is the minus 6, times 50. This is the total charge, right? Now, when it's in parallel connection, okay, so which means it should share the same weight, loading, it should share some load on both, right? The total charge should remain unchanged, so this charge should equal to 26 times this way plus this 40 times this way. Am I right? Total charge remain unchanged. Right? Total charge remain unchanged. So that's this is the charge on this one. This is the charge on this one. Means the charge will be okay. So that you cancel out this side. So what you get here is this one. This times this is 130, right? 130 equal to 26V plus 40V. So this is equal to 40V. Then what is my V? V is actually 4 divided by 3. What so 30 divided by 4. This is V. And when you get V times this guy and the charge on this, V times this one and charge on this. Okay? This is 50. This plus this is equal to. This is a lot. 50. This times this rate is 1,030. Okay, so 1,300. 1,300. Okay, so this should be 65 divided by 2. This should equal to 65 divided by 2. Okay, so 65 divided by 2. So you get the rate on the half of the charge this one and this one. So what's the question asked here? Oh, this is already done. Oh, for rate on the about 32.5. Yeah, okay. So this is how we solve this question. Yeah. You're clear? Yeah. So I think each step is very clear. What you have to realize is this is parallel connection. If two capacitors connected across each other, that is parallel.
But if you connect, doesn't mean that the voltage across the voltage share is the same as voltage share.
In parallel, always the same.
Yeah.
Voltage always the same. In series, charge always the same. In parallel, voltage always the same.
series 的 Q 的。In series 有个问题，把因为 core capacitor 靠 force 以前的，它是 always power。or otherwise how can the capacitor force each other? So in series connection, you need a voltage. So if you just, for example, if you connect two capacitors connected in series without a voltage, that doesn't make any sense. Because it's not, for example, this is also a power connection. You know, because it's also this guy connected here connected. This is also power. So only this you connect with other things, not directly connected with us in series. But if you remove the voltage of series connection, does not has regime. Because which means now it was disconnected on one side, you cannot charge it. So core capacitor connected across each other, that's only component. Because it's head connected head, bond or radio connection. So even this or this connection, if this there, okay, as I said, if there does not have any voltage, okay, then I will have. Yeah, it's this is part because you can say here direction to here direction. This is part of it. Okay. Good. Okay, next. Good.
Hello? Hello? Okay, Daniel, any question?